Okay, do you remember adding hydrochloric acid to a double bond? How did that happen? First, the proton added to the double bond and you formed the more stable carbocation. Then the chloride came diving into that carbon and formed a bond there. Well, dienes can do this too. If it's a non-conjugated diene, you're just going to get double addition, as you can see in the. But if it's a conjugated diene, the pi system works together, so some special things can happen. The mechanism is the same in that the proton adds to one end of the pi system, and you get an allylic carbocation. Remember, allylic carbocations are stabilized by resonance, and so there is resonance between the two ends of the pi system. Both of them are shown here. When that carbocation forms here, it's also down here. Now we show resonance so that there's positive charge here and then positive charge here, but really what it is half the positive charge is here and half the positive charge is there because of the way that the pi system works. Well, then the bromine has two places it can dive into. It can either dive into this number 2 carbon. If the hydrogen is considered to add to the 1 carbon, then the bromine would be adding to the next carbon, or the bromide could go all the way to the end of that molecule and add there. We call it when the bromide dives in to the carbon next to where the proton added, we call that 1,2 addition. And if it dives to the other end of the molecule, we call that 1,4 addition. So this is, the double bond used to be here, so we call this proton here, bromide there, 1,2 addition. The double bonds used to be here and here, proton added here, and the bromide added down there, and we call this 1, 2, 3, 4 addition. The carbocation has the following orbitals. It actually has a molecular orbital system because there's 3 carbons in there, 2 of them a double bond, and 1 has an empty p. So there's 3 p orbitals, and they form 3 orbitals, one of which is non-bonding. This is the lowest energy orbital, and since it has a positive charge, there's only 2 electrons in the pi system. So where is it that the bromide is going to come in? Since this is the non-bonding orbital system and it can take electrons, the bromide, which is a HOMO because it has our orbitals are all occupied, comes in and it's going to either attack here or here. Notice this is where the hydrogen added. This is the pi system that's left. The bromide can either come here, and it's equal energy to do either of that. What is the difference is that, well, there is a little bit more, because this is more substituted, there is a little tiny bit more of the positive charge here, because that positive charge can be stabilized by this carbon over here that has a bond to hyperconjugate here. So there's a little bit more a positive charge here. When the proton adds, the bromide is hanging nearby because it doesn't like to lose track of that positive charge. It likes to stay nearby. And so it's very quick and easy for it to just go pew and add to this positive place. So that's a lower energy addition. But when the bromide waits and doesn't dive into this carbon right away but travels all the way down here, you get a more substituted double bond. And although the transition state is higher because the bromide has to actually move away from positive charge to come down here, the product is more stable because it's more conjugated, more substituted. So we have 2 products then that can be formed. In many of the reactions, there's no contest between the product, that the kinetic, that the fastest formed product is the most stable product. But here there's a difference. The fastest formed product is actually less stable than the one that takes more time to form. So we've got a little bit of yin-yang going on here. And when we've got yin-yang like this going on, we can grab a hold of the reins and direct the reaction where we want it to go. So if we want it to go to the kinetic control reaction, it's faster, so we do things that make it hard for the other reaction to occur. If we want the one that is more stable, we do things to give the bromide time to go to the other end. When we have the one that forms fastest, we call it the kinetic control product. And it's because the transition state is lower, even though the product may be a higher energy. And we are able to make the kinetic control product form when the reaction is irreversible. With this reaction, we can make it irreversible by lowering the temperature. And by lowering the temperature, we make the fastest reaction, the 1,2 reaction, happen. But if we want the bromide to travel to the other end of the molecule to give us the lower energy product, what we do is we hold the reagents in reaction situation longer so that that lower energy product has time to form. In order to get this, what we do is we pick conditions that give a reversible reaction, because the kinetic one is going to happen faster regardless. But if we have the conditions so that the reaction can reverse, eventually the more stable product will start to form and accumulate, while the kinetic control product will start being used up by reversing the reaction and going to the more stable state. So let's look at how this looks with the reaction profile. The kinetic control product has a lower energy, so it's in blue. And the reaction's faster because the transition state is lower. The thermodynamic control one, the reaction is slower and the transition state energy is higher. If you are doing the faster reaction and you're making it go all the way to the product and we don't let it reverse, it doesn't matter what the energy of the products is, because the faster reaction is going to occur if the reaction can't reverse. However, if the reaction can reverse, the energy of the products matter. Now, I'm cutting off the top of the curve. We're going to reactants to products, and the top of the curve where the transition state is cut off. What we're looking at is the energy of the products only. In blue, that's the kinetic product. It's less stable, but its transition state was faster, and you get there quickly. The thermodynamic product, the one that is slower to form, it's more stable. And it will never form if you're just allowing the reactants to whoop one time, because the faster reaction will occur. But if you allow this one to reverse, eventually this one, which has a higher transition state, will start accumulating products here, because this is not going to go backwards. It's too high a jump up to that transition state. So this, if you have the temperature higher, this reaction goes quickly, but then it reverses too. And then eventually the high energy transition state is breached, and you start making product with a lower energy. So when we're looking at these reactions, if the temperature is high, the reaction is going to be reversible, because then the transition state can be reached. if the temperature, the reverse transition state, can be reached. But if the temperature is low, the reaction is going to be one way, because as soon as it goes over that hump, it's not going to return and go up to that higher transition state. And some reactions, like this hydrobromic acid addition to a conjugated diene, are reversible at low temperatures, irreversible at low temperatures, and reversible at high temperatures. So we can control which one goes. Let's look. The 1,2 addition is less stable, but it's formed faster. We call this the kinetic control product. Low temperatures prevent the reaction from reversing, so the fastest product is made. 1,4 addition is more stable, but is formed more slowly. So if you have high temperature conditions, you make the reaction reversible, and initially the 1,2 product is formed, but its addition reverses, and the more stable product will start accumulating, because you have reversal, forward, and as soon as you form a 1,4, it's not going to reverse anymore. It's going to stay, because it's such a huge transition state jump. So we have thermodynamic control at high temperatures. So this is what we remember when we have a reversible reaction. We get kinetic control at low temperatures and thermodynamic control at high temperatures. So let's look at the entire reaction profile to better understand this. Here is the energy of the diene and the hydrobromic acid before the reaction. The addition of the proton has this transition state energy, and then it drops to a carbocation intermediate. That carbocation intermediate now has 2 pathways possible. If it's low temperature, this will form fast, and this product will accumulate, and you will not get the other product. 1,2 addition will occur. It added here and here. But if the temperatures are high, you have this form, but then it reverses. And then you have this form, and then it reverses. And then, once in a while, this will form, and it doesn't reverse. And pretty much all of this that formed reverses, and then this accumulates. So we end up making the 1,4 product at higher temperatures. Kinetic control at low temperatures, thermodynamic control at high temperatures. So, what is a 1,2 addition reaction product here? Draw it. Okay, if the proton adds here, the bromide's going to add there, because that's 1, that's 2. Alternatively, you could have the double bond here and the bromide here. It's equivalent. There's no difference in the products. What is the 1,4 addition product? Well, if the hydrogen adds here, the double bond will be between where the double bonds used to be, and then the bromide will be at the end of the other double bond. That's 1,4 addition. So which of these is the kinetic product? Well, the kinetic product is that's formed fastest. Fastest addition occurs 1,2. So the kinetic control product, the kinetic control product is 1,2 addition right here. Which one is the thermodynamic product? Well, the thermodynamic product adds 1,4, and that's 1,4 addition. Which product is formed under high temperature conditions? High temperature conditions cause reversibility. Reversibility causes a more stable product to form. The one with the substituted double bond is more stable, and so that is the one that is formed. Which product is formed under low temperatures? Low temperatures cause the kinetic product to form. The kinetic product is 1,2, the less stable but faster formed product. And that is the low temperature product.